A big hi to all the students. Let's start with our next session today, that is transition metals and coordination chemistry. Transition elements can be defined as those elements which have incompletely filled d orbitals in any of their oxidation states. They occupy d block in the periodic table. Since they exhibit transitional properties between highly reactive elements of the s block, which form ionic compounds, and the elements of p block, which mainly form covalent compounds, hence the name transition elements. Their general electronic configuration is N-1, D1 to 9, Ns 0 to 2, where N is the period number and the numbers in the superscript denote the number of the electrons. On the basis of the period number, transition elements have been classified into 4 series. The first series is the 3D series, which starts from the element scandium and continues till zinc. This series consists of 10 elements. The second series is the 4D series, which starts from yttrium and ends at cadmium. This series also has 10 elements. The third series is the 5D series, which starts from lanthanum and continues to mercury. This series also has 10 elements in it. The fourth series is the 6D series, which consists of elements from actinium onwards. This series is incomplete as more elements are being discovered, and we must note that the elements after actinium are synthetic. Now let us have a look at some of the general characteristics of the transition elements. They are all metals. As compared to s-block elements, they are hard, malleable and ductile. They have high melting and boiling points as compared to the s-block elements and the p-block elements, except zinc, cadmium and mercury. Melting and boiling points are related to the binding energy of the atoms, which is highest in the middle of the series. Transition metals are good conductors of heat and electricity due to the presence of delocalized electrons. The atomic volumes of transition metals are low as compared with the s-block elements. They are densely packed with high coordination number. On moving through a series, the density increases with maximum density in the middle of the series and then decreases subsequently. Atomic volume follows the reverse order, that is, it decreases to a minimum in the middle of the series and then increases subsequently. On moving down a group, the increase in covalent and ionic radii is very low due to lanthanide contraction. The atomic radii decreases on moving through a period. However, it is almost constant from chromium to copper due to the screening effect. Their ionization potential values lie between those of the s-block elements and the p-block elements. Thus, they are less electropositive than the s-block elements, but more electropositive as compared to the p-block elements. Transition metals exhibit a wide range of positive oxidation states. When a transition metal atom forms a coordination complex, the oxidation state it acquires depends on the energetics of the process. The removal of electrons for ion formation requires energy, whereas energy is released when compound formation takes place. The valence shell electrons in transition metals occupy N-1, D1 to 9, Ns 1 to 2 orbitals. These orbitals are of comparable energy, and the energy required to remove successive N-1, D1 to 9, Ns 1 to 2 electrons is not very high. The requisite energy is easily available in the formation of more and more chemical bonds. This table shows the common oxidation states of the members of 3D series, that is from scandium to zinc. In general, on moving through a period, the number of oxidation states of each ion increases up to the middle of the period. After that, it decreases because the later elements experience stronger force of attraction between their protons and electrons due to the increase in their number. For example, in the 3D series, manganese shows the maximum number of oxidation states, that is up to +7 in its period. Otherwise, in general, osmium and ruthenium exhibit the highest stable oxidation state, that is +8. The oxidation states which are denoted in red color are less common. The most common and also stable oxidation states of transition metals are those in which the orbitals of the metal are fully filled, half filled, or empty, because these are the most stable electronic configurations. Usually, the transition metal ions with oxidation state above +3 cannot exist in aqueous solution. Ions in higher oxidation states act as oxidizing agents, whereas those ions which are in lower oxidation states act as reducing agents. The transition metal compounds are colored if in that particular oxidation state it possesses at least one unpaired electron. When the formation of a transition metal complex takes place, the ligands increase the energy of the orbitals of the metal, causing them to split into two groups. One group is of the orbitals at high energy level and the other group is of the orbitals at low energy level. The unpaired electron can be excited from one energy level to the other energy level within d subshell. The electron will absorb light radiations of that wavelength, which provide just that amount of energy that is required for its transition from lower energy level to higher energy level. The energy required for such DD transition falls in the visible region of the spectrum. Now, some of the wavelengths are absorbed due to transition, whereas the others are reflected back. The color of the transition metal compound is that of the reflected light.